Next up, we have Michael Wyatt. Constraining reionization using Lyman alpha emitters.
All right, hi everybody. My name is Michael Wyatt. I'm a graduate student at UCLA, and I'm going to talk to you about some work that's a collaborative effort between myself and my advisor, Steve Ferlinetto, as well as some of our collaborators at the SNS in Pisa and the University of Tokyo. And I'd just like to start with a little bit of a walkthrough of kind of the structure of the talk. I'm going to start with a little bit of background on how and why we constrain reionization using Lyman alpha emitters, and then I'll introduce this idea of persistent homology and the specific statistic known as the Betty curve, or the Betty zero curve. And then what I would like to do is compare this new statistic, the Betty curve, to existing statistics for this purpose. And of course, for that, we're going to need to simulate some Lyman alpha emitters during reionization and create some mock observations for something that might be possible with the Roman telescope, and then compare the constraining power of these methods to one another. And hopefully I can convince you that this new statistic, the Betty curve, is a promising method for this purpose. So, okay, right, reionization, of course, is the epoch of the universe where the first luminous sources began emitting light, and this light travels outward into what was the neutral IgM and forming these ionized bubbles, which we think of as growing over time, becoming large enough so that they interconnect and eventually fill the entire universe. And studying reionization is interesting because if we can constrain this process, then these observations on these tens or hundreds of megaparsec scales can inform or tell us information about processes on the small scales within those galaxies that are actually doing the reionization. And so one way to do this is by using observations of Lyman alpha emitters, which I'm showing you here from a simulation where the Lyman alpha emitters are of course shown as the white dots. And you'll see that as we look back in time towards higher neutral fractions, shown here with the XH1, then the number of Lyman alpha emitters that we see, of course, becomes smaller, but also the ones that we are able to see exist only in these increasingly rare large ionized bubbles, because the Lyman alpha photons can travel freely through the ionized IgM but are absorbed by the neutral IgM. So the idea is that if we can somehow quantify how clustered these Lyman alpha emitters are, then we can use that measurement in order to constrain the timing of reionization, or what the global neutral fraction is at the redshift of that observation. Okay, so how exactly do we quantify this clustering? There's plenty of different ways to do this. The most common is the two-point correlation function, or in 2 dimensions, the angular correlation function. I assume that most people are familiar with this idea from various different topics in astronomy. One that's probably a little less familiar is known as the void probability function. And this one's pretty straightforward. We just imagine plopping down circles of some radius on our observation and counting the fraction of those circles that are empty or void of Lyman alpha emitters, and we can do this for different radii and create a curve that way. And then, of course, there's this persistent homology, which is the, I say, new strategy that I'm proposing, though it has been used in cosmology in the past, though as far as we're aware, not for Lyman alpha emitters. So I'd like to talk about what the heck this persistent homology actually is. And before I get into this, I'd like to just start by saying that this is really quite a deep mathematical topic that's used in topological data analysis. And what I'll describe here is really just the simplest form of this statistic. So I think there's a lot here to unpack that might be useful to look in more detail in the future. So if we imagine we have a collection of points, which might be our Lyman alpha emitters, what we're going to do is we're going to draw circles around each of these points at increasingly larger radii, and we're going to connect the points together whose circles intersect, and then we're going to group those points into these little clusters that we call components. So at the smallest scale, we have the same number of components as we do points, and then the number of components decreases monotonically till eventually all of the points are connected into a single component. And then what we do is we represent this process with something called the Betty zero curve, which simply tracks the number of components that we have as a function of scale, and hopefully you can already imagine how this might be sensitive to the clustering, where the particular shape or the slope of this curve will change depending on how tightly clustered or sparsely clustered these points are. Okay, so going very briefly over our simulations for the sake of time. In order to simulate our mock observations of Lyman alpha emitters, we're using 21 cm fast, which is a semi-numerical model of reionization. And at the end of the day, we basically get 2,000 independent slices of the universe. And I should say that these are all run at the same cosmological and astrophysical parameters, so the only variance that we're looking at here is from cosmic variance. Each of them are around 4 degrees squared at redshift 7.2, which is the redshift we'll be looking at. And what we have are the locations and the observed fluxes of our Lyman alpha emitters, where those observed fluxes depend on the ionization fraction of the universe. And in terms of our mock observations, we're just going to go with a simple uniform selection of our Lyman alpha emitters above some observational flux limit, which I'll come back to in a second. And we're going to look at, in this case, global neutral fractions of 40%, again at redshift 7.2. So in terms of getting the observational flux limits, we're going to look at 3 different possible survey scenarios, and these all come from a paper by Wald et al. 2024, who did some nice detailed forward modeling of potential Roman observations, specifically for looking at Lyman alpha emitters. The first I'll call the small area deep survey, which is around a degree squared with a total observing time of around 12 days. The next is larger but shallower, about 4 times in area, but the same amount of survey time. And the third is somewhere in between, again, a 4 degree squared survey area, but this time a longer survey time. And you might notice that the high latitude wide area survey, at least deep tier, is not present here, and that's because we just found that with the flux limits that are expected in that survey, we're simply not finding enough Lyman alpha emitters, at least to use the statistics as we use them here with the simulation volumes that we have available to us. Okay, so now we can compare our different statistics across these different survey configurations, and we'll start with our small area deep survey. And on the right-hand side, I've plotted the 3 different statistics. The x-axis shows the scale in co-moving megaparsecs, and the y-axis in each panel shows the value of each statistic. The 2 different colors show the results for a universe that's 35 and 45% neutral. And you might be able to sort of barely see the difference visually there, but of course we want to look at this in a bit more quantitative way. And to do that, we're going to use the Fisher information, which gives us a quantitative measure of how constraining each of these statistics is, in this case for the global neutral fraction, xh1. And we're going to take advantage of a property of the Fisher information, which says that 1 over its square root tells us the minimum possible uncertainty that we can achieve using this statistic on our global neutral fraction. Okay, so this is exactly that. The different colors here show the results for the different statistics. Again, these are all for, at first, the small area deep survey. I've listed again the observing time at the top and the number of Lyman alpha emitters that we might expect from this survey configuration. And the y-axis here again shows that minimum uncertainty that we can get using each of these statistics. So I'd like to point out just a couple of things. First is that the angular correlation function and the void probability function perform about similarly, somewhere around 0.17. The Betty curve does slightly better than each of those, somewhere around 0.15. And what I've plotted in black here is the uncertainty that we can achieve if we use if we simultaneously fit to all 3 statistics. And this is interesting because we're actually achieving slightly better constraints by doing that, which means that the Betty curve does provide independent information to the other 2 statistics, and it's not just a redundant reforming of the same statistic. We can compare this to the larger, shallower survey, which is again the same observing time. And although we have a wider area, we're getting fewer Lyman alpha emitters and correspondingly less sensitivity across the board, though again the trends are very similar comparing the different statistics to one another, where the Betty curve outperforms the other 2 statistics and the combination of the 3 outperforms any individual statistic. And probably no surprise, the larger medium survey gives us better constraints than the other two. And in this case, at least in absolute terms, the statistics perform more similarly to one another. Now, of course, one other interesting question that we can ask within the context of Roman is how much better can we do on these constraints if we use three-dimensional rather than two-dimensional versions of these statistics? Because with Roman, of course, we'll have spectroscopic measurements for the locations of these Lyman alpha emitters. And so all the statistics that I've discussed can be just as well defined in 3 as in 2 dimensions. And so we can just include the redshift information, repeat the same calculation that we just did. So again, this is the small area deep survey in 2 dimensions. And in 3 dimensions, we see sort of modest improvement across the board and similar trends in terms of performance of each of the statistics compared with one another. And similarly for our larger survey. Now, hopefully this is not too disappointing. Maybe some people were hoping that the constraints that we might be able to get from including that 3-dimensional information might be more significant compared with the 2-dimensional. But I do want to point out here that these results are for the constraint that we can get on the neutral fraction at a single slice of the universe. And I think the real benefit that we'll get from the Raman spectroscopic measurements of these Lyman alpha emitters is that we will have slices that are back to back to back. And so you can do something, for example, like constraining a model of reionization that you have constraining all the redshifts simultaneously, or even doing something as simple as enforcing monotonicity of the global neutral fraction can improve your constraints in that case. Okay, so I'll pop up my conclusions here. Hopefully, I've been able to convince you that the Betty curve is a promising method for constraining reionization using Lyman alpha emitters, both with Roman, but hopefully also in general. I'm almost out of time here, so the last thing that I'll say is that unfortunately we were not able to get this paper up before the conference, but I do hope that it will be up, hopefully in the next month. So if you are interested, do be on the lookout for that. Please feel free to reach out with any questions or comments you may have, and complaints can be addressed to my collaborators. Thank you.
Thank you. We have time for one quick question. Yes, in the middle there.
So thank you for this talk. Just a basic question for you. You say that the Betty zero curve is not redundant, or I guess degenerate, with the 2-point correlation functions and the void finder. Is it because it is using different information about the Lyman alpha emitters, or is it because it is just a different way of calculating the same information?
I would.
Do you see what I'm asking?
I think so. I don't think it's just a reforming of any of the statistics, though it is. They're all quite similar to one another, right? They're probing similar structure and similar kinds of information. The Betty curve is. I'm not sure I have a fantastic answer to your question. I do think it contains independent information. I don't think it's just a reforming of any of the other statistics.
Okay, I can ask you about it later.
Sure, yes.
Topological data analysis is really cool, so thank you for this.
All right, let's thank Michael again.